Section: Introduction. In this section, we discuss the importance of extrapolation in machine learning, which allows us to make predictions beyond the data we trained on. Our focus is on how to predict the label for a target sample that is not part of the training data. For instance, if we trained our model on images of dogs, we want it to recognize dogs in new situations, like different lighting or angles. We note that while humans can adapt easily to these changes, machine learning models often struggle with even slight shifts in data distribution. This issue has led to significant research efforts. One approach, unsupervised domain adaptation, deals with changes in the data distribution but relies on certain assumptions that may not hold in our case. Similarly, domain generalization assumes we have multiple training distributions that cover the target distribution, which is not always feasible. We also highlight test time adaptation, TTA, which focuses on adjusting models for individual test samples. However, much of the existing research in TTA lacks a solid theoretical foundation. Some studies have proposed frameworks to understand distribution shifts, but they typically require multiple overlapping source distributions, which doesn't apply to our situation where we might only have one out-of-support sample. To tackle this challenge, we introduce a latent variable model based on a minimal change principle. We assume that a latent variable influences the observed data, allowing us to separate the changes into two parts, one that is outside the training support and another that remains within it. This helps us simplify the complex shifts in the data to manageable changes in the latent space. We identify two scenarios based on how the changing variable affects the data: dense influence, where all aspects of the data can be influenced, and sparse influence, where only a few aspects are affected. Our first condition for dense influence states that if the changing variable affects all dimensions, we need the different classes to be clearly distinguishable to make accurate predictions. Our second condition for sparse influence suggests that even if only a small part of the data changes, we can still recognize the class of the target sample. Through our theoretical framework, we gain insights into how the smoothness of the underlying data structure, the distance from the training data, and the nature of the changes interact. We validate our findings with synthetic data experiments and explore how our insights can enhance existing TTA methods, particularly in improving autoencoder-based approaches. In summary, our contributions include framing the extrapolation task as a problem of identifying latent variables, providing guarantees for this identification under different conditions, and proposing enhancements to existing TTA methods based on our theoretical insights. We support our claims with empirical evidence, demonstrating the practical applicability of our theory. Section Summary. In this section, we address the challenge of extrapolation in machine learning, where we aim to predict labels for out-of-support samples by formulating it as a latent variable identification problem. We propose a model that captures complex changes in observed variables through latent variables, providing identification guarantees under varying conditions of influence, and demonstrate the practical applicability of our theory through empirical validation and enhancements to existing test time adaptation methods. Section: Related work. In this section, we discuss related work on latent variable identification for transfer learning. In the literature, we often see that latent variables generate observed data, like images or text, through a generating function. However, the nonlinearity of deep learning models complicates the recovery of the original latent variable. To address this, some researchers assume that each data sample has an auxiliary label, which causes significant shifts in the distribution of the latent components. This approach does not consider shared information across distributions, which is common in transfer learning tasks. Recent studies have proposed a way to separate the latent variable into an invariant part and a changing part, where the invariant part's distribution remains constant across different distributions. They demonstrate that both parts can be identified, allowing us to use the invariant variable for domain adaptation. However, their methods depend on having multiple diverse distributions, which limits their applicability to extrapolation problems. In contrast, our theoretical results show that we can identify the invariant variable using just one source distribution and a single out-of-support target sample, with only mild assumptions about the generating function. This directly addresses the extrapolation challenge. We aim to make predictions on a target sample that lies outside the source support. While having more target samples would help us understand the distribution shift better, we often only have one sample to work with. Thus, we focus on this difficult scenario. Reliable predictions for out-of-support samples are challenging without additional structure. In real-world situations, humans often extrapolate based on minimal changes, recognizing familiar objects despite significant background changes. For instance, if someone has only seen a cow in a pasture, they can still recognize it on a beach, even with a different background. Here, the cow represents the invariant variable, while the background change corresponds to the changing variable. Extrapolation fails if all dimensions change or if the changing variable significantly alters the object's appearance. We define our data generating process based on this minimal change principle. The latent space consists of two parts, the invariant variable and the changing variable. The invariant variable captures shared information between the source distribution and the out-of-support target sample, while the changing variable accounts for the shift from the source support. The variables together generate the observed data through an invertible function, and we assume that the label comes from the invariant variable, reflecting that certain factors do not affect the object's class. Our model adheres to the minimal change principle by ensuring that the out-of-support nature of the target sample arises from only a subset of latent variables and that these changing variables do not influence the label. Section Summary. In this section, we discuss the challenges of identifying latent variables in transfer learning, particularly when dealing with extrapolation from a single target sample outside the source support. We propose a model that separates invariant and changing variables, allowing us to make reliable predictions by leveraging shared information, while adhering to the minimal change principle to ensure effective extrapolation. Section NRIPS_2024. In this section, we explore how extrapolation can occur when we can identify the true invariant variable, which we denote as C, in both the source distribution and the target data. This identification allows us to create a classifier that maps C to the corresponding labels in the source data. Since the invariant variable in the target sample is included in the source support, we can apply our classifier directly to the target sample. Therefore, our main task is to identify C in both the source and target datasets. We define identifiability, specifically block-wise identifiability, which is essential for successful extrapolation. We state that the true invariant variables for any two samples are equal if and only if their estimates are also equal. Next, we present two sets of conditions that help us identify the invariant variable, C, and discuss their implications. We need to match the target sample with source samples that share the same invariant variable values. This matching allows us to assign labels from the source to the target sample. The differences between the source distribution and the target sample arise from the changing variable, which may not be present in the source support. It is important to make appropriate assumptions about how this changing variable influences the data so that we can still identify C. We introduce the Jacobian matrix of the generating function and describe how the dimensions of the data are influenced by the changing variable. If the changing variable affects many dimensions of the data, it becomes harder to identify C, because there may not be clear indicators of it. Additionally, the extent to which the changing variable deviates from the source support significantly impacts our ability to retrieve C. We will formalize these conditions and highlight the trade-offs involved. We also define our statistical estimates for the generating process, ensuring that our estimation respects the true generating conditions. We begin by examining cases where there are no limits on the number of dimensions influenced by the changing variable, which we refer to as dense shifts. In the context of images, these shifts can include global transformations like changes in camera angles and lighting that affect all pixel values. Section Summary. In this section, we explore the conditions necessary for identifying the invariant variable, C, that enables extrapolation from a source distribution to a target sample. We discuss how the influence of a changing variable, SS, on the data can complicate this identification, particularly when SS affects many dimensions of the data, leading to dense shifts that obscure the signatures of C. Section NRIPS_2024. In this section, we provide a proof sketch for our approach. We estimate the generative process using maximum likelihood estimation on the source distribution. Under certain assumptions, we can identify values of a variable on the support, meaning that if two values are equal, their corresponding identifiers are also equal. This indicates that all samples from a specific source share the same identifier value. Our goal is to maximize the likelihood of the target identifier to align it with one of the discrete values that has a significant probability. Given our identification, this means we assign the target sample to a specific manifold associated with the correct identifier. To ensure we are on the right manifold for the target sample, we need to confirm that our selected identifier matches the target identifier. We achieve this by choosing the estimated model that minimizes the distance from the off-support nature of the target sample, adhering to the principle of minimal change. This, along with our assumptions, guarantees that only the correct manifold can effectively represent the target sample, aiding in the desired identification. We can implement these constraints using Lagrange multipliers, with the full proof available in the appendix. Next, we explore scenarios where the changing variable affects only a subset of dimensions, which we call sparse shifts. For instance, in image distributions, these shifts might involve local corruptions or background changes that do not impact the main objects in the image. We maximize the likelihood to assign a value to the target identifier. By leveraging our assumptions, we identify the dimensions that remain unaffected by the changes. This means that the unaffected dimensions in our estimated variable match those in the true model. Additionally, our assumptions ensure that the dimensions in the target sample cannot be achieved by any other identifiers, confirming that our estimated value corresponds to the correct target identifier. The full proof is also in the appendix. Importantly, unlike cases with global shifts, we do not impose constraints on the out-of-support nature of the changing variable, which we verify through empirical evidence. Lastly, we address the issue of regularization. Since our objectives involve both the source distribution and the target sample, and the source distribution may not be available during adaptation, aggressive updates to the target sample could distort the source information in the model. To mitigate this, we propose regularization on the source pre-trained model during adaptation to ensure minimal changes and preserve source information. We demonstrate this with low-rank updates and sparsity constraints, highlighting the benefits in our experiments. In this section, we also conduct synthetic data experiments focused on classification to validate our theoretical results, with additional experiments on regression presented in another section. Section Summary. In this section, we outline our approach to estimating the generative process through maximum likelihood estimation, ensuring that the identified values of the latent variable correspond correctly to the target samples while maintaining minimal changes to the source model. We also discuss the implementation of regularization techniques to preserve source information during adaptation and validate our theoretical results through synthetic data experiments. Section NRIPS_2024. In this section, we compared our method with IMSDA and a model trained solely on source data. The results, shown in a table, indicate that our approach consistently outperforms both baseline methods, which performed nearly at random across all settings. This supports our theoretical findings. The results for IMSDA reveal that applying domain adaptation methods directly to extrapolation tasks can have negative effects due to the absence of the target distribution during training. We also conducted real-world experiments to confirm our theoretical insights and practical algorithms, with additional results available in the appendix. We integrated an entropy minimization loss into the MAE-TTT framework and compared it with the original version. The results demonstrate that adding entropy minimization steps significantly improves the performance of MAE-TTT, highlighting the beneficial interaction between autoencoding and entropy minimization as outlined in our theory. Furthermore, we incorporated sparsity constraints into the advanced TTA method, Tesla S. Although our theoretical results are based on a generative model, we showed that these implications also apply to discriminative models. For our experimental setup, we tested on the CIFAR10C, CIFAR100C, and ImageNet-C datasets, following the protocols for Tesla and Tesla S, both with and without training data information. During pre-training, we used ResNet 50 as the backbone and trained it on clean datasets with joint contrastive and classification losses. In the test time adaptation phase, we followed a sequential TTA protocol that maintains the same training objectives throughout testing. To promote sparsity, we added low-rank adaptation modules to the backbone, limiting adaptation to low intrinsic dimensions. Additionally, we implemented a masking layer with a sparsity constraint to filter out unnecessary changes, with more details in the appendix. In our results analysis, we summarized the average error rates across 15 corruption types for all datasets. We observed that the sparsity constraints consistently improved performance over the current state-of-the-art methods, Tesla, Tesla S, across all datasets. The lightweight nature of these constraints and their consistent performance enhancements make them a valuable addition, showcasing their potential as a flexible module for improving existing TTA methods. To explore the trade-off between shift scope, dense versus sparse, and severity, we simulated various levels of corruption severity and region sizes, evaluating a classical TTA method, TENT. We introduced impulse noise to the CIFAR10 dataset, varying noise levels from 1 to 10. By cropping different region sizes for corruption, we analyzed classification error curves under these conditions. Our findings showed that classification errors increased with higher noise levels and larger regions. Notably, for larger block sizes, dense shifts, performance significantly declined as severity increased, while it remained relatively stable across severity levels in the sparse shift scenario, confirming our theoretical conditions.